Hey, boys and girls. Yep. So this is about abiogenesis, and it covers a couple of things. So about a year and a half, maybe 2 years ago, I was on Stinky Saints stream with Tony, putting brain, fucking shit for brains, Tony, whatever, the abio guy, the guy that's always talking about abiogenesis and raving about it. And
you mean talking against abiogenesis?
Yeah, okay. Right. And two things came out of that stream. Number one, that I don't read my books because I only read 2 out of the 10 abio books that I showed Smokey. And the other thing was, this idea that speed of pudding, that's where the whole thing started. And I just thought, and it was on this stream here. And if you guys can hear it, I'm just going to play the part, I think, where that kicked it off. And maybe we can, and then because it's all connected. Okay. There are 2 narratives that Rebecca and et al. And the whole creationist gang put out about abiogenesis, and both narratives are false, straw men, bullshit. And I just want to address them. So
desperate.
Yep. Seems how we don't have many listeners, we can just listen to this. Just trying to get some ceiling popcorn on.
That's fine. Everyone's got ceiling
that voice. I haven't heard that voice. I want things to be equal. I want this to be equitable. Yeah.
Go ahead, sir.
Anyway, how do I reply? Let's see. What would you have them do, Tony? How would you do these experiments? You're a chemist. How would you do the experiments to explore how some of these compounds could be created?
You have to start out with a random mixture of chemicals, which would have to relate to the early Earth conditions, similar to what Stanley Miller did in 1953. And that experiment really didn't show much. There's a lot of problems with that. So I would say to simulate early Earth conditions, you have to start with a random mixture of chemicals. You can't start with hand-selected chemicals. For example, chemists select all left-handed amino acids when they're doing their protein folding experiments. They buy synthetic kits from other chemists, and these molecules are carefully prepared in such a way. So they allow the chemist to succeed. And the reason is because the molecules have been purified and hand-selected and handled in such a way that it's showing intelligent agency, not unguided natural chemistry.
Okay, so I have 2 questions about that. First is, how in the hell do you know what the early conditions of the Earth are? And the second one is, do you know what pudding is?
We know what would have been found on the early Earth, and the experiments that have been shown never succeed. But if you want to say, okay, well, we don't know, that would make your side even more moot and uncertain. Chemists would be guessing even more than they are now.
Yeah.
So chemists have removed oxygen. They said the atmosphere was reducing. We haven't. They said that all what Miller produced back in that 53 Miller experiment was chaos. Basically, what he produced was death.
Okay, so that's enough of that. So what I was asking him is, okay, and it's kind of hard to unwind this. Okay, when I asked him, what would you do?
Is this the live speed talking?
Yeah, it is.
Okay, sorry.
Yeah, I know. Do I sound the same? Weird. I hope not.
Well, there's a difference, but you sound younger in that one. But
yeah, I was younger. I was a lot younger back then.
But anyway, I just was making sure.
Okay. So number one, we don't know what all the prebiotic conditions were back then. Number two, Tony was implying that we should just take any random mixture of chemicals and see what happens, okay? And there is virtually no way to do that in a laboratory setting. Now, what they do is they will take certain chemicals, and they're not, he's also implying that they go and buy these purified chemicals so that they can succeed in their experiment. That's not what they're doing. They're starting with purified chemicals, and then they pick conditions, and then they see what results from that. And now we know one thing, and that one thing is going to apply to one tiny little slice, one tiny little speck of the prebiotic earth. So you understand that the earth was not pudding. It wasn't just a homogenized mixture of random chemicals.
I think it's also like they expect you to like do like perhaps cook live almost. They are expecting you to cook live, but it's not like that, because it's more like the scientists want to know exactly what is happening, and that is why they choose like a few chemicals at the most to understand what is happening. But if you put in a random set of chemicals and you don't know what is happening, it's very difficult to determine what's happening. Yeah.
I always get the feeling, anytime, even if somebody is a quote unquote chemist by trade, when they start referring to the Urey-Miller experiment, they're acting as if more was expected from the Urey-Miller experiment than the production of organic compounds. It's like it was just a big slimy stew of death. Well, what was the stated goal of the Urey-Miller experiment? If things were dead, or if it was deadly, if that could be true, and the Urey-Miller experiment still have met its goal. And from what I hear is there were actually more compounds, like organic compounds, that were actually produced than were discovered initially, because they kept all the material, and then now that we have better equipment to detect and measure and all that, they found even more materials that were produced in the Urey-Miller experiment. So it's actually better news. But I wonder what the stated goal of the Urey-Miller experiment was, and if it had a stated goal.
To find out if we could create amino acids, and they succeeded wildly beyond their expectations.
Yeah, and so any other complaints about it are just stupid.
They created 10 of them.
Yeah, it's like, I invented a car. Well, it can't fly. Well, cars, that wasn't the goal, So
I don't even know if amino acids were even the goal. I just think they were just trying to let's have an atmosphere, which we think was the atmosphere back in the day, but of course now we know better. But in any case, they were trying to simulate conditions and see what happens, and it turns out, we didn't expect that.
Yeah. Did not expect 10 amino acids.
Although as someone who leans more towards the hydrothermal vent scenario, I of course have some opinions about the relevancy of the Miller-Urey experiment. But that's beside the point.
Right. Okay, now if you were to start out with a random mixture, I don't know what the hell he means by that. For
homogeneous, or put it in a blender kind of thing. I don't know.
Any random mixture that you started out with would occupy exactly one little section here in the prebiotic earth, and these sections are these are quadrillions and sextillions of squares wide and long. So I mean, there are that many different prebiotic environments that basically could have contributed, right? And of course, we're trying to reduce it. We're trying to narrow it down and focus in. And we're hoping to find, that with this the environments that will produce something, and that's what every single abiogenesis paper is about. They start out with a fixed, they start out with a fixed environment so that they understand what they're starting out with. And then they try to go one step and they try to do something. and they come up with a result. So now we know that that step works, right? That step can happen at a yield greater than probably 0.01% or 0.1% or whatever. So if we get any kind of a yield nearing 1%, I think that's worth writing home on. So now we know that that little step for this particular environment worked, right? So we have to basically unwind all of these different environments, and you can see how hard the task is. Now, the other key narrative that Rebecca comes up with, and Sel and everybody keeps saying is, oh, they write about it in the press like abiogenesis is solved. And I don't think any abiogenesis researcher has said that we have solved abiogenesis.
I've never really read a paper or an article that says it's solved. I think they'll say, well, scientists, think, or scientists speculate, but I don't really think anybody says it's a for sure, solved problem, because it isn't. And I think that's just, once again, kind of desperate. They're real sensitive to it because they don't want it to be true, or they don't want it to be solved or happen, and people are giving it credibility, and that's against my religion.
Exactly. You see, I can read minds, and what they're really saying is that the press is implying that this is not an impossible thing, that
it's not laughable, or
it's not impossible. And that drives them crazy because that takes away one of the planks that they have holding up their God. And so they're really upset about that. It's like, oh my God, they implied that we're making progress. And every single paper is progress. But if you imply any progress at all, they freak the hell out, because that takes away their big plank underneath their God hypothesis that, it couldn't have happened without God. Well, in order for them, the burden of proof is on them to prove that all of these steps are impossible. So anyway, and the next thing that we have is David Deamer. This was just released today, right?
I got the notification for it today.
Okay.
From Google.
Yeah.
Google Scholar Alerts is a really great thing. If there's a topic that you really like, you can set up a Google alert and get alerts whenever something comes out about it. I've got one referring to like early hominids and things like that. Today I got one from Reasons to Believe. I think that's a ministry or something like that, but usually it's a pretty good, a pretty good source of information.
Okay. So let's see. So anyway, this paper is a request by David Deamer that we do start with messier environments, and that we do put together more and more concoctions. Now, if you go back to this Rob Stadler on Rebecca's stream, he was constantly implying that we have to take that, not only do we have to start with things that we find in organisms today, but we have to look for products that are only in organisms today. And that is a false narrative, because more than likely, almost certainly, the first basically protocells and prebiotic life would have had amino acids that we do not recognize. It may have had nucleic acids that we don't recognize. It would have had heterochiral compounds. It would have been sort of a little bit of a mess. And out of that mess, basically due to this chemical natural selection, there would have been, over a period of about 500 million years, it would have started to narrow down to the life compounds that we're used to. That would have taken 500 million or a billion years to basically narrow down. So we are not looking for just life chemicals that we recognize today. That promotes the ridiculous idea that we're going to mix some stuff together in a test tube and we're going to create a cell. And that's never been the plan, basically. But actually, a lot of abiogenesis researchers are also suffering from that same paradigm. And one of the things that Deamer is requesting here is that we extend our, that we widen our experiments to include more random mixes. So anyway, can anybody read this? Who can read better and speak better than me? I'm not enunciating well tonight again.
I can do some reading, but I won't read from the screen. So you might have to holler when you want me to stop.
Yeah, do the abstract.
Abstract. Most experimental results that guide research related to origin of life are from laboratory simulations of early Earth conditions. In the laboratory, emphasis is placed on the purity of reagents and carefully controlled conditions, so there's a natural tendency to reject impurities and lack of control. However, life did not originate in laboratory conditions. Therefore, we should take into consideration multiple factors that are likely to have contributed to the environmental complexity of the early Earth. Excuse me. This essay describes 8 physical and biophysical factors that spontaneously resolve aqueous dispersions of ionic and organic solutes mixed with mineral particles and thereby promote specific chemical reactions required for life to begin. And the keywords are origin of life, messy conditions, laboratory simulations.
Right. And there's also a strong bias by David Deemer toward the geological volcanic pools that he likes. So that's so that is, you know, somewhat behind this paper. But we will refer to the result of such processes as resolution. Okay, this brings us to the question being addressed.
Can I ask a quick question, Speed?
Yeah.
I'm just really feeling the need to time out Otangelo so he'll just shut the fuck up and listen rather than okay. Yeah, shut the fuck up and listen, Otangelo, and then after your timeouts are over, maybe you can, you know, complain or whatever.
Right.
So there you go. And Spooky and Groove, if you can monitor that. I'm not censoring Otangelo. I just want him to shut the fuck up and listen for a while rather than spew out all his negative Nelly shit.
Yeah, we're putting him in the corner.
Yeah.
We'll deal with him when we have time to deal with it. But can you start reading the paragraph that begins with "that brings us to the question being addressed"? It's
Turn to me or Nestling?
You. So third paragraph down.
That brings us to the question being addressed in this essay. How could orderly structures and functions emerge that led to the first forms of life? The answer must involve physical and chemical processes that occur even in messy conditions. We will refer to the result of such processes as resolution, meaning that relatively pure compounds are produced and then concentrated in such a way that they can react despite the complexity of their surroundings. However, it is helpful to realize that messiness can be divided into chemical and physical components, and that there are synergistic combinations in which certain physical conditions can promote specific chemical reactions. Each of the following subtopics are examples of such interactions.
Okay, so they call it resolution. So we're starting with one of these many environments, right? And we've got a mess of chemicals, and there are a mess of reactions. And as Rob Stadler pointed out in one simulation they did with this alchemy program, they ended up with, like, after seven phases, they ran into 38,000 different compounds. But what they're talking about is the emergence or the resolution of certain compounds that end up becoming concentrated and are present at a higher than normal yield. So they end up basically amounting to maybe 1% of the solution, but it's just 1% where something is happening, where we proceed from one step to the next step, and that's kind of what we're looking for.
I don't know, have you ever heard of, like, autocatalytic cycles?
Yeah, exactly.
Yeah.
They're
Or autocatalytic sets, more popularly. Like, it says that if you have, like, a number of molecules, if you add more and more chemical substrates, then the probability of having an autocatalytic set increases, and eventually you will reach, like, 100% certainty if you add more.
Right.
Yeah.
Yeah. So in addition to these things that I drew here, there's also this other basically dimension of these things where they're going through all these different cycles, like lunar cycles, are going through day-night cycles, they're going through tidal cycles, they're going through wet-dry cycles, they're going through heat-cold cycles. And they're, I think he points it on the paper, but there are just wide ranges of temperature. Like the solar, basically the sun was putting out a lot less energy at that point, and there was likely to be freezing going on. But there was also meteor strikes and volcanoes popping up. So you had everything going from molten lava to frozen water, and you're doing so in cycles. So we're not only looking at all of these sextillions of different microenvironments, we're also looking at these cycles going down in another dimension off my graph here, my two-dimensional graph, which would be the time cycle. So,
hey, show that figure 1, the bumpus hell.
Yeah,
clay formation there. It makes a really good point about, you know, how many billions and billions and trillions of little labs there were in early Earth, what with, you know, all the volcanic activity going on.
Yep. Yeah, and I mean, just looking at that, you can imagine how many different laboratories it would take, how many different experiments and reactions it would take to simulate what's going on here and unwind all of the complexity that's going on.
Yeah, and I know Nestle prefers the hydrothermal vent scenario, and think about how many billions and trillions of hydrothermal vents there were under the ocean.
And what if basically life required both of these hypotheses together? Because there would be mixing. There's, you know, the ocean, the tides are bringing all that stuff up onto the shore, and it's washing back again, and you know, so there's a lot of intermixing going on. There's a lot of.
I'm not convinced of that, but still, yeah.
Yeah. Well, these guys are in one camp, and you're in the other camp, and you guys are gonna, you know, fight it out. But
I tend to take like a thermodynamics first, because you need this equilibrium to drive life into existence, and when you break up the equilibrium that is required, then you run into trouble.
Yep. Anyway, okay, physical self-assembly processes tend to resolve complex mixtures, and all I highlighted here is, well, do you want to read the 5 points that he puts out, Scott?
Sure. Now, what page are we looking at? Okay, here we go. A number of concerns arise when a chemist considers a natural environment in comparison to a laboratory one. Is it that section?
Yeah, those 5 items.
Some of these are related to the composition of a mixture, while others come from physical variations such as temperature, pH, ionic solutions. Let's see. Oh, somebody time Otangelo out. Once again, he's not listening. He just wants to blabber on in the side chat, saying shit that he means he obviously has not gone over the literature. So
back in the corner.
Moderator in here. Thank you so much. Dessel's among us. Hey, Dessel.
Hi, Dessel. Okay.
But anyways,
yeah. By the way, the Rob Stadler thing was meant to be basically a comeback when Dessel was on Bread of Life, and he did a wonderful 2.5-hour presentation, and Rob Stadler took notes and basically countered every point he made. So anyway,
cool. Well, and I'm sure we'll get a counterpoint from Dessel. Probably already have in one of his papers that he read.
I'm sending that man an invite just in case.
Okay, so desired reactions cannot occur if a solution is composed of so many solutes that the reactants are diluted. Side reactions interfere with yields if other solutes are present as potential reactants. If the temperature is too low, there will be insufficient activation energy, while too high temperatures will result in what a chemist refers to as tar.
Yep.
Tar, mate. Rather than controlled condensation reactions that synthesize specific bonds such as esters and peptides, elevated temperatures and high activation energy drive the formation of multiple random bonds that produce the intractable intractable polymers called asphalt and tar. Extreme pH ranges markedly affect the kinds of reactions that can occur and their yields. High salt concentrations, particularly of divalent cations, or is that how you pronounce that? Cations?
Cations, yeah.
Such as calcium precipitate anions that are essential for life. Calcium, for instance, reacts with phosphate to form the insoluble mineral apatite.
And apatite? I think apatite, I think. And anyway, Stadler was talking about these divalent minerals and claiming that they destroy membranes. Do you know anything about that, Ness?
Oh, sorry, can you repeat that?
Okay, he's claiming that divalent cations destroy lipid membranes, that they tear apart lipid membranes, which would be kind of surprising because we have all those divalent ions in our cells, and they don't tear apart our membranes. So I don't know what.
I have recently watched a presentation by Nick Lane, and he shows that if you have like a mixture of different types of lipids, then they will be more stable.
Yeah. Yeah, and
if you only have one, like if you only have one clean, like pure type of lipid, then it will be less stable than having this, like, a mixture of different lipids.
Yeah, and James Tour made the point that there's he had once said that basically it was too messy and there would be too many types of lipids, and in the another statement he said elsewhere, they would all be the same kind of lipid and it wouldn't be as stable. So I mean, he like contradicted himself on this.
Yeah.
We know there was a mixture of many types of lipids, basically.
And life still uses many lipids in their cells today too. Like
right.
I think they use a different ratio depending on the temperature and the environment. Like I think like thermophiles you have a very different type of ratio than usual life.
And then the approach described here is to realize that certain physical properties of complex mixtures can add order to a disorderly system, thereby promoting specific chemical reactions. So what we're looking for is the emergent order from the disordered, massive mess of things. And finding those particular ordered pathways is why they do each individual purified experiment to find one link in the chain, right? So we're looking for that emergent pathway. So anyway, what else do I have here? 3 conditions are key to resolving messy reaction mixtures. And you might want to read all of that paragraph there, Scott. My reader?
Alrighty.
You're a good reader.
Here we will focus on 3 conditions that are ubiquitous in the laboratory, but seldom invoked as solutions to deal with messy conditions on the early Earth. The conditions are related to concentration, water activity, and temperature. For instance, when organic chemists synthesize an ester, I knew a lady named Esther once, she was really sweet. They will mix pure, highly concentrated solutions of organic acids and alcohols rather than dilute solutions in an aqueous phase. The obvious reason is that water is a product of the condensation reaction that forms ester bonds, so the highest yields require that the water activity is low. The chemist will also heat the reaction mixture to provide activation energy that increases the rate of the reaction. An important question is how linking bonds could be synthesized on the prebiotic Earth to provide the more complex molecules required for life to begin. Examples that have been explored in the laboratory include polyesters, peptides, and depsipeptides. Some of these words are familiar.
Yeah.
Taking a lesson from organic chemistry, the potential reactants must be concentrated, dry, and at an elevated temperature. There's only one natural environment that meets these requirements: hydrothermal pulls on the subaerial volcanic land masses.
Now you're going to piss Nestle off.
I know Nestle's probably fuming right now. Precipitation provides fresh water distilled from a salty ocean, and the water in hydrothermal pools undergoes continuous cycles of evaporation and re-wetting. If organic solutes are in the water, they will become extremely concentrated films on mineral surfaces during the dry phase of a cycle and then redissolve in the wet phase. Finally, the temperature is elevated, but typically less than the 100 degrees Celsius boiling point of water. That's 212 degrees Fahrenheit for those who...
us Americans.
Yeah, for us Americans. The lower atmospheric pressure at higher altitudes. An important point is that even though a variety of solutes might be present in a messy solution, only those solutes capable of self-assembly or forming linking bonds will serve as reactants for polymerization, while the other solutes will be inert. Given the significance of concentration, we can now consider processes that can increase the local concentration of potential reactants.
Okay. And I think that that's all very, very optimistic.
Can I make a few comments about previously? Can you scroll back again?
Okay. Yep.
About the, like it says, taking lessons from organic chemistry, the potential reactants must be concentrated, dry, and at an elevated temperature. It's not true, because life does that all the time. It's not in a dry environment when it does that. So how does life do it? It lowers the water reactivity by molecular crowding.
Yeah,
and I think that Dessel also mentioned the so-called water paradox in his talk with Rebecca, and how water reactivity is lowered in like rock-water interfaces in the hydrothermal vents, where you can have dehydration reactions even in solution.
Okay.
Yeah.
Fair enough. Yeah, and I think again he almost made the mistake of optimistically believing that the pathway is going to not be very long.
Yeah.
You know that.
There's also a beautiful talk by someone called Eric Smith. Like it's one of the authors that I recommend of the book. You know, like the origin of life, or the origin of the biosphere. I think you have the book himself. Like he says that there is an approach by organic chemists which he calls chasing equilibrium, where they say like, condensation reaction is not favorable in an equilibrium conditions with water, but it is favorable in dry conditions. So let's chase that equilibrium state to get that reaction going. However, how life does the reaction is not chasing equilibrium. It is by coupling a disequilibrium with ATP and ADP and coupling that with the condensation reaction. That's how life does it, and that needs to be explained.
Yep. And the other thing about equilibrium is that if you have changing physical environments and you have changing localities, basically you can beat that equilibrium by stuff basically frothing over from one environment to another, or crossing from one environment to another, where the equilibrium equation changes, and now you've got something that basically hangs on. So
yeah, it's basically like life drives many reactions in biochemistry that are not thermodynamically favorable on their own, are coupled with a thermodynamically favorable reaction, with, for example, ATP to be turned into ADP and a phosphate, and that coupling between those two reactions is what drives the system to go uphill, so to speak. Yeah.
Right. Even in the cell, you have microenvironments that consist of little these biocomplexes. You know, that where things will basically be sequestered physically one from another. They don't have a membrane surrounding them, but yet the environment within the cell, there are multiple environments where different things happen based on different concentrations. So, Anyway, okay. Polar versus non-polar oils and monolayers at the air-water interface. Furthermore, some of the hydrocarbons present in unrefined oil are likely to be amphiphilic compounds that have both polar and non-polar moieties in their structure. And I don't know, say, okay, maybe you want to read that one too. Go ahead, Scott, number 4.
Okay. The whole thing?
Yeah, just the first paragraph.
First paragraph? Okay.
Yeah.
Number 4, the first paragraph. We tend to focus on water-soluble polar and ionized solutes when we think about constituents of messy mixtures. But we should also consider non-polar compounds such as aliphatic and aromatic hydrocarbons and their derivatives. One of the simplest resolutions in a messy environment is the fact that oils are relatively insoluble in water and are also less dense. Hydrocarbon oils, therefore, tend to separate spontaneously from other solutes and float on water surfaces. Furthermore, some of the hydrocarbons present in unrefined oil are likely to be amphiphilic compounds that have both polar and non-polar moieties in their structure. Amphiphiles are classified as surfactants because they spontaneously accumulate at air-water interfaces as monomolecular films and reduce the surface tension as a result.
Yeah. And now we have we have the inside of that those amphiphiles, and we have the outside, and then we have just inside and just outside. We have the surfaces basically. So there's like 4 different environments that happen when you have these amphiphilic compounds. So that's another key thing. I think the point I'm making is that there are lots of microenvironments. It is not pudding, like people seem to imagine. You know, we're
not a
trying to
smoothie.
Not a smoothie. Yep. And let's see, what do we got here? Yeah, they show basically fatty acid here, which is polar. It has a water loving part and a water hating part. Okay. And then let's see. So the Murchison meteorite is a mixture of silicate mineral grains with approximately 0.1% by weight of soluble organic compounds that include monocarboxylic acids, amino acids, alcohols, polycyclic aromatics, which are really important, and we don't think enough about them, such as pyrene and fluoroanthene, and even some purines, such as adenine, which are nucleic acids. So
I have some comments about that as well. It's in the same talk with Eric Smith. He gives attention to even though you have very different conditions in space. Like space, we have very high energies bombarding these meteors in space, and also after that you have very, very cold temperatures to keep that system stable. And it's very different conditions found in normal temperatures here on Earth. But even these differences, you have very similar compounds, and that indicates that there are paths of least resistance in biochemistry, according to Eric Smith. So what this shows is that these chemicals are easily selectable in a terminology that would be used by, for example, Otangelo inside. Like he said, like, how would you select these chemicals? But it turns out that chemistry has a lot of information in of itself, where some chemicals are easily produced by the structure of the chemistry itself, the very physics. And one of the funniest comments by Eric Smith is that chemistry is one of the most information-rich systems in the universe, and that's why physicists are so afraid of it.
Especially organic chemistry. I mean, the amount of information just in any random mixture is incredibly high.
Yeah.
Rebecca talks about, where does the information come from? It's already there, Rebecca. It doesn't have to come from somebody putting it in there.
I think they're expecting like Lord of the Rings to be inscribed inside the molecules or something.
But when they talk about information, they probably mean something like semantic meaning, like words, statements by intelligence. But of course, that's not information in science, like in information theory, for example, or even in thermodynamics. It's not that. It's not meaning. It's a very difficult concept to understand.
Yeah. Stadler admitted that basically that there was catalysis even with small peptides and small divalent cations, and he admitted to that. And then later on went on to say that no, it had to be like this big long chain of things, and the probability was horrible, and you couldn't have it. And so he kind of like speaks with forked tongue on that stuff.
Well, I agree with Otangelo about the meteorites coming down to Earth. Like, I also don't think it's relevant to abiogenesis, because of course I'm a hydrothermal vent guy. But yeah,
yeah. But then I think I saw a calculation as to how much organic material came from meteorites during the what is it called, the late bombardment, and it was like incredible how many millions of tons came from meteorites. So they definitely had a part.
No, I don't think so. Like it's not just the ingredients. You also need the pattern itself, and also the disequilibrium pattern itself also that drives the system, and that is very difficult to have unless in hydrothermal systems. Like the only thing that I see that is most similar to the disequilibrium found in life that defines like the for example the pH gradient from the membrane, that drives ATP synthesis, that is only found in hydrothermal systems.
Yep. You know what my favorite hypothesis is about abiogenesis?
Go ahead.
Do you guys know what my favorite hypothesis is?
I do not.
I don't know.
Neither do I.
Mm-hmm.
There you go.
Oh, that Dessel mentions that in some models there is a relevance with meteor impact when it comes to like and of course when you have an impact that can facilitate like the interaction between water and olivine to form serpentinite, and serpentinization is a very important process. If I'm not, did I get it right, Dessel, about how impacts can cause the hydrothermal systems to form, right? Or maybe I'm mistaken about that.
Is that Handbook of Astrobiology by Kolb? Vera M. Kolb, that one? I think. We'll have to take a look at that. I will. Yeah, I think so. Anyway. Okay. So what else did I highlight here? Oils and amphiphiles that accumulate on aqueous surfaces would be exposed to UV light, and a variety of photochemical reactions would then occur. So they're talking about this layering and these lamina, basically, and the effects of UV light. And of course, you hydrothermal vent guys are going to hate that. Oh, sister.
It's not just me that hates UV light. Like life in general hates UV light. That's why it makes things like melanin to protect itself.
Yeah, but organic reactions love UV light.
No, not really. Actually, no.
Really?
No.
There's a lot of things.
It's again. I mentioned the concept of chasing equilibrium before. Like, you can chase equilibrium, and one of them is if you add enough energy to the system, like UV light, you can force some reactions to go, but UV light has also the capability of breaking the reaction back again into other stuff. So what you need is more control, and catalysis is what gives you more control of the system, and that is why life uses catalysis to facilitate reactions, and it uses very specific energy states to have the energy go through, like again, the pH gradient and ATP with ADP. That's also one important system. Yeah. So UV light is not it's not really close to what you need for life, at least in my opinion.
It's what you need for a lot of weird chemistry, though.
Weird chemistry, yes, but not life chemistry.
Life is weird chemistry.
That's what like Nick Lane calls such chemistry as Frankenstein chemistry, because it's very alien to what life actually uses.
That's my favorite hypothesis, Frankenstein chemistry. Okay, widen your view, everyone. Okay, do you want to go ahead and read this paragraph, Scott? It's right underneath figure 3.
Figure three. Okay, yeah.
Figure.
This is another example of orderly structures emerging from disorderly. That one?
Yep.
Comma. Messy conditions. Membrane-bounded compartments were essential prerequisites for the origin of cellular life, and it seems likely that micelles and vesicles were abundant in the prebiotic environment. Assuming that various I'm sorry, what?
I was just saying that it depends on the concentration. Like if they are very dilute, the lipids won't form vesicles or micelles, but when you reach a certain concentration, they will self-assemble into micelles and vesicles, yes.
Gotcha.
Yeah.
Assuming that various polymers were also being synthesized, the microscopic membranous compartments would be able to encapsulate random peptides and oligonucleotides to generate protocells. I practiced that one earlier today. Oligonucleotides to generate protocells. Although protocells are not alive in the usual sense, they represent an essential step towards life.
And this next sentence is yelled out in blue.
Okay. I underlined mine on my copy, but each protocell differs in composition from all the rest and represents a microscopic experiment. Most are inert and their components would be recycled, but a few might happen to have properties that allow them to survive stresses imposed by the environment. Populations of protocells would therefore undergo the first stages of selection and evolution.
Yep. We got another paragraph for you if you're ready.
Okay, sure. Yeah. Another absorption as an organizing factor.
Mosquito.
You have a mosquito?
I have a mosquito. I'm going to have to catch it. Okay. Go ahead.
Oh, I have a question about like Dessel has some commentary in the chat. Maybe he can join. I don't know if he can join.
I sent him an invite. I sent him an invite.
Who did you invite?
Dessel.
Oh yeah, hey Dessel. And thanks for staying on top of people who aren't listening, like Otangelo. Many physical and chemical processes cannot occur in the absence of a threshold concentration. So a physical process that specifically increases the local concentration of a potential reactant can act as a catalyst. Clays are aluminum silicate minerals that have an enormous capacity to absorb polar and ionic solutes.
Ionic.
What did I say? Iconic? Ionic solutions. As shown in figure 4, they are microscopic particles that are often present as layered structures called smectic phases.
Smectic means cleaning phases. Cleaning.
Okay. All right. I thought that was just kind of a made-up word.
Yeah, and the next paragraph says something pretty fucking amazing. So think about it. Here we go
with some amazing stuff and a really cool picture. Various clays have surface areas ranging to from 100 to 400 square meters per gram.
Per gram. Think about that.
Wow. How in the well, I'm sure it's
what I want to point out is how non-intuitive that is. I mean, we can't even wrap our minds around that. That basically clays have all of this surface area because of because of how finely ground they are. Oh, so I think we have Dessel here.
James Ferris and co-workers tested whether clay surfaces could promote the polymerization of activated nucleotide monomers. In their initial studies, they reported that when the nucleotides saturated the surface of morillonite clay, oligomers ranging up to 10 nucleotides could be detected. Later research demonstrated chain links as long as 30 to 50 nucleotides. Am I done reading, or do you want me to read this last paragraph?
Yeah, you're done.
I'm wondering if maybe like the mineral surface inside alkaline vents could do the same thing as that.
Yeah.
Maybe you know something about the place.
You have the same incredible surface area. I mean,
Yeah.
the surface area is just incredibly high, non-intuitively high. I mean, I don't think that is intuitive at all. So, anyway.
A chemist accustomed to reactions in aqueous solutions might be disappointed by the lack of polymerization in a solution of activated nucleotides. Did I say nuclear again? Nucleotides. Pretend you're an island. Nucleotides.
You're from
But
Texas.
then would be surprised to see polymers appear when the solution becomes more complex and messier with the addition of clay. The catalytic effect of clay materials or minerals is an example of why messy conditions should be explored more extensively. There may be other surprises in store.
Yep. And Dessel has joined us. Hi, Dessel.
Hello, Dessel, sir.
Howdy. My connection's really bad. Can you guys hear me all right?
Yeah, you're good right now.
Pretty good. You get a little bit echoey, but pretty good volume. You're doing good. So,
okay.
Anyway, so do we want to go further, or do you guys just want to discuss? So, because we got these eutectic phases, which refers to.
Oh, I had a question to Dessel about like if he knows anything about how the mineral surfaces inside the alkaline vents could do the same thing as the morillonite clay that was previously mentioned. Like it can.
I'm sorry. Give me a moment, Nestleg, because even though it looks like you guys can hear me okay, you guys are chopping out for me really bad. Give me a second to close out some of the million tabs that you saw earlier, so that way maybe this will work okay. And I'll come back in just a minute and I'll listen to your question. All right, so give me a second.
Use bookmarks.
Okay, you might want to read these two paragraphs, Scott. Eutectic phases.
Okay.
Eutectic, I believe, refers to basically melt freeze, easily implemented melt freeze cycles. I think is that correct, Nestleg?
Yeah, I've heard of freezing cycles, but again, it like when something as alien as that is proposed for the origin of life, I cringe.
Well, eutectic would refer to when you put a snowflake on your hand and it easily melts. That's like a eutectic phase. It's an easy melting phase.
It says in the first sentence that the eutectic phase occurs when an aqueous solution freezes. So I think it's the opposite what you mentioned. Anyway, go ahead, Scott. Go ahead.
Thank you. The most common eutectic phase occurs when an aqueous solution freezes. As ice crystals form, they tend to exclude solutes, which become highly concentrated films between the crystals. The concentrating effect is similar to evaporation because reactions can occur that cannot proceed in a dilute, disordered solution. The power of eutectic phases to promote reactions was demonstrated by Menard et al., who froze complex mixtures of nucleotides at minus 18 degrees Celsius. The nucleotides were chemically activated as imidazole esters and spontaneously formed ester bonds to polymerize into strands 5 to 14 nucleotides in length. Atwater et al. Also tested freezing temperatures as a way to promote non-enzymatic polymerization of RNA. They used in vitro selection to evolve a cold-adapted ribozyme that was capable of catalyzing the template-directed synthesis of a 206 nucleotide RNA sequence. The reaction was markedly promoted by a cycle of freezing that concentrated the reactants in a eutectic phase. Bada et al. proposed that the early Earth may have passed through a snowball phase related to decreased solar luminosity at the time. They speculated that freeze-thaw cycles related to bolide impacts may have promoted reactions that synthesized organic compounds required for life's origin. Eutectic phases associated with freezing would have played a role by concentrating reactants such as HCN, NH3, and aldehydes that would then undergo Strecker synthesis to form amino acids. Although this idea remains speculative, it does illustrate how another physical process, freezing and thawing in this case, has the potential to resolve specific reactions in complex conditions.
It's a similar solution to the wet-dry cycle is proposed. Of course, I have a similar problem to the wet-dry cycle as this idea. But yeah, let's continue.
Yeah, and I think the next paragraph we can skip, but it's about these complexes that form with guanine, I think, and a few other things. And Rob Stadler, that was one of the things that he complained about. And they're claiming that it's one of the things, these quadruplexes that produce these crystals are basically another thing that we have to consider as a mechanism rather than a problem. So, and yeah, you're right, Otangelo. I just spotted a comment. It is speculative. That's what it's all about. We're speculating. We don't know. This is a very new field. We don't know. Every paper is a new piece of speculation. What your job is, Otangelo, is to prove to us that something is impossible. You go do that, and you get back to us when you prove that.
Yeah, you have like speculation, and then you reformulate your hypothesis. You do some tests, maybe speculate some more, change your hypothesis, do some more tests and experiments.
God created exactly as how we create machines and factories. Like God has factory lines and construction sites. And that's how he did it.
Yeah.
I've no idea.
Yep.
Anyway, that's all. Are you back? Do you have good connection now?
It sounds better, yeah.
Oh,
Awesome.
have you heard about what was previously said about the freezing cycles to concentrate these substrates? Have you any opinions on that? Like I have a similar opinions as about the wet-dry cycles.
You asked me about freeze-thaw?
Yeah, the eutectic process that you mentioned, Scott. Yeah.
So basically, my thing is like with these kinds of cycles, one of the things that Stadler was putting out there, he attacked the nucleotide pathway that I offered on the grounds that the Kim and Kim paper involved a dry down phase. And one of the things that I was trying to mention, and I sidetracked myself in that original presentation, I started talking about serpentinization, and then I listed like a couple of papers. And then when I did that, I'd forgot my actual point about serpentinization, which was, if you check out Nascimento Vieira 2018, it's this paper called The Ambivalent Role of Water at the Origin of Life. It talks about serpentinization, how it mimics wet-dry cycling, how it leaches up all the water in the area as it precipitates minerals. And then once that process is done and all the water is leached up, so you get to this dry down phase, and then the ocean water gradually leaches back in again and starts the process up once more, which is why I felt perfectly justified to include, the Kim and Kim paper along the pathway. And when I went to this mini symposium, Martina Prainer, right? She wrote a geochemical analog of carbon fixation by hydrogen or something. Oh man, it's this paper where they synthesize pyruvate and a bunch of other stuff.
Yeah. Yeah.
I figure you should. Do you know what I'm talking about there, Nestlig? It's like a popular article for the hydrothermal.
I think I've seen it. Yes, I think. Yeah.
Yeah. Well, she's a co-author on the Nascimento Vieira paper, and she was at the conference, and so I asked her about it. I said, do you really want to stick by this, like describing serpentinization as like mimicking wet-dry cycles? And she insisted that that she thought she still considers that to be a good perspective in terms of like looking at serpentinization in that way. So I don't like with the freeze-thaw cycles. Like I feel like I'm not. It looks like they're able to accomplish a lot with it in terms of forming this stuff.
Mm-hmm.
I'm kind of I
feel like is this a red herring? Like you could do that, but is this process relevant to the origin of life? That's always a question you can always ask, of course. So that's my thinking about the freezing and thawing cycles. Because like, I also don't know if it would be possible or it would be prevalent on the Hadean or even the Archean Earth, because it was pretty warm back then, if I'm not mistaken.
They're all over the place with that one. Like you can read these geologists who think it was really hot. You can read geologists who think it was snowball Earth. You could read geologists who think that it was a climate that was pretty much similar to today. They're all over the place. They in my personal opinion, they really got to get their shit together when it comes to the Hadean environment, which is why I was trying to stress when I was talking to Rebecca about the things that they at least have common ground on. And they have enough common ground where you could use a hydrothermal vent model, and there's no disagreement that they were widespread during the Hadean. But as far as the actual temperature and the atmospheric composition and all that stuff, there's still wide-ranging disagreement.
It would be very CO2 rich, at least relative to today, of course, because it would be very relatively acidic ocean, like pH 6 or something like that. The ocean, it's pretty rich in CO2 at least.
Yeah, that whole thing about the Kadoya arguing for like meteor impact, shuttling CO2 out of the atmosphere and stuff. That's why when I was talking to Russell, he offered me those papers by Lupton, talking about the highly purified liquid CO2 that's bubbling up around the hydrothermal vent sites. That acidifies it at the very least locally. But for him, he's arguing that this goes on so much during the Hadean that you're pretty much guaranteed an acidic ocean at that time. So, but
you also believe the Hadean ocean was like a water world, right? Like no land masses, pretty much.
Yeah, he's a water world guy. He's arguing with. Do you know? Have you checked out any Koranaga? Jun Koranaga?
Not familiar. Sorry, not familiar.
They're the two heavyweights battling it out right now in the literature, going back and forth. Russell's arguing.
Russell and the other guy. Yeah.
Yep. So they're arguing back and forth whether or not there was land.
So Dessel,
go ahead. Sorry.
Dessel, you had that interview with Russell?
So when I tried to have that interview with Russell, he had so many technical issues, and I jumped through so many different hoops to try to help him out in being able to get his PowerPoint up. And like he couldn't download Chrome, he couldn't get his Firefox to work with StreamYard. We ended up having to jump over to Zoom, but he didn't tell me when I signed up to use Zoom that when you sign up without payment, it only lets you stay in for like 15 minutes. And so we start the freaking interview, and 15 minutes later, it tells me that it's going to drop out. And so then that happened. And so like the following day, he emailed me and he's like, hey, look, sorry for all the tech trouble. Would you like to reschedule? And I said, sure, let's reschedule. And so I think we're supposed to do it again October 6th. And I went and I bought a new laptop, and I had him send me his PowerPoint so that way I can do it now. So that way there's no technical issues.
Please email me before you do it when you finally set it up so that we can talk about it. And hopefully you're going to leave it up on your channel for more than a couple of days.
Yeah, that one. that one for his sake, just for Russell's sake, I'm going to leave that one up, and that's actually going to be my last YouTube video. I'm going to do one responding to Dr. Stadler, and I'm still kind of up in the air about whether or not I want to do the whole historicity of Jesus thing, responding more to Jordan. I'm really tempted to do that, but at this point I'm just so fed up with YouTube that I think I might drop that one and just do 2 last videos, one responding to Stadler and the Russell interview.
Yeah.
One thing I want to mention about the the landmass thing. I've seen several arguments about the Earth is losing its water to space, and also also losing its water to the crust of the Earth, because as the Earth cools down over eons, the crust becomes more water absorbent, so it's also losing water to that. So there is the argument that Earth used to have a lot more water in the past, and also since the crust was warmer in the past, it was less buoyant. It was less able to have the high, thick continental crusts that we see today. So those arguments seem to suggest that there were no dry land, or almost no dry land masses in the Hadean, at least. And I know you have any opinions about that. Yeah.
So so those are the kinds of arguments that Russell uses. So check out, because I'm actually, even though Russell's been really generous with his time with me, I'm actually gunning for a land-based hydrothermal model. So I'm actually rooting for Koranaga to be right about this, but we'll see whether who comes out on top. But what Koranaga argues back is that in the literature that Russell relies on, particularly he uses this paper by Montu et al., which talks about basically the mushiness of the initial crust, but it's a model.
It was much less viscous, I think, right? The mantle was more fluid.
Exactly.
Yeah.
Yep. And so, but the thing is that Montu, he doesn't factor in, and this is stuff that I have to learn a little bit more about. Maybe actually you know more about this than I do, but the counter argument is that the work done by Montu that argues that it's about 500 million years of this mushiness of the crust. He doesn't factor in the Rayleigh-Taylor instability. And this can actually lead to a much more rapid solidifying of the crust. And so Koranaga says that this is not actually a good argument because it doesn't factor in certain things that could lead to its drying down and solidification. And so that's one of the main arguments being thrown against Russell's use of Montu. And so, so we'll see how this ends up turning out. Like I said, I personally, I'll try to be quick about this and tell you why I'm gunning for a land-based model. The first thing is that
salinity issue, of course. Yeah, the salinity that you were mentioning before, right?
What's that?
It's the salinity issue, right?
The salinity is definitely a huge thing because if you have an ocean with really high salt content, that obliterates thermophoresis. And I'm not saying that thermophoresis is it's like an all or nothing thing. You still have mineral adsorption, which is something I didn't talk about during my talk with Rebecca, but that's been shown to do a lot in terms of polymerization. And there's been a lot of stuff done Benner, who I recently talked to and had a very bad interaction with. I didn't like that guy very much, but I spoke with him, and he has this paper on RNA adsorption on mineral surfaces, and this has to do with the whole purity thing in a lab. Well, he went out to actual sites across the U.S. and Canada and so on, and got a bunch of actual natural samples to test whether or not they adsorb as effectively as laboratory purified samples. And so, for example, you take pyrite, which is relevant to hydrothermal vents. That has the natural samples have a 95% efficacy of RNA adsorption. So like, you know, pointing out that, yeah, like the natural samples are working very well. So yeah, it's just like a further effort to show that this applies not just in the laboratory, but in the natural world. But so you have that option there. But if you don't have thermophoresis, that's one of the things that that I think is a really good way to also give you chiral bias and like the onset of homochirality. It's this temperature gradient that induces spontaneous mirror symmetry breaking. Now, again, there are other models that might be able to account for that. You know, like amino acid catalysis of carbohydrates. You know, that induces a chiral bias. Preferences of mineral catalysts inducing chiral bias and stuff. But the actual ability for thermophoresis to drive this like and really strongly augment it, you know, where it's like a continuation of non-equilibrium thermodynamics all the way through. That's why I really like this model, because it's just a continuation of this same underlying principle that's like at the base of why I think both you and I support hydrothermal vents. It's this idea of life being a far from equilibrium system, and its most distinctive characteristics arising from that fact. And so, you know, that's why I'm kind of gunning.
Okay, if there is anything that can be called all or nothing for me, it's like the thermodynamics aspect of that. Like if you
me too.
Yeah, if you propose a system that is thermodynamically flat, no way.
Yeah, agreed.
Yeah.
Yep, you and me are 100% on that one. Yep. Yeah, so that's why, and there's another aspect to this, and I'll wrap up my whole spiel on this one with this last point, is that with the idea of like these meteorite-induced hydrothermal systems, you also have the opportunity for to apply this work that I'm actually really excited about with, I mentioned her during the program, Harpreet Kaur. She's working in the Moran lab. And you're also, just to ask you, like, have you checked out any of Joseph Moran's stuff? Of course, like you must know him because you've referenced. You've referenced.
I've referenced the paper, and when talking to like CRISPR, I think I referenced his paper. Yeah, he's awesome. So like she's working under him right now, and what she's been able to do with Palladium is freaking awesome. Like she's according, and I asked Moran about this, and he confirmed it. It's going through peer review right now. She's getting at room temperature using even trace amounts of Palladium, the entirety of the metabolic cycles. And so like that's just like freaking huge, right? You mean the core, like the citric acid cycle and the phosphate pentose phosphate cycle and such, or?
Yes, I believe that she mentioned in her talk the citric acid cycle, and I think she also referenced, you know, like the reverse Krebs cycle, and acetyl-CoA pathway, all that stuff that the vent guys are really focusing on too. So like she's getting the whole shebang there, as well as potentially, I think she might have mentioned some of the other pathways. It might have been the PPP and other ones, gluconeogenesis, etc. But don't hold me to that because I can't remember for sure. But she's getting like robust results from using even trace amounts of the metal. And it's true that you can find trace amounts of this metal like at hydrothermal systems. There's this one paper that I have, it's on my phone actually, it's not on here, where they detected Palladium at certain hydrothermal vent systems, certain ophiolites. But I think that if you want to like incorporate that into your model, because it's so rarely found, like I wouldn't like make a bet about that finding it at a hydrothermal event. I think the likelihood would be higher.
It's also the thing like go ahead.
Sorry. I'll just last sentence here is I think the likelihood would be higher if you're dealing with an impact-induced hydrothermal system because you have Palladium also on these meteorites. And so like the likelihood of finding Palladium in a natural environment would be much more increased if you're dealing with like that kind of interface there with a meteorite coming in, delivering Palladium and a hydrothermal vent, potentially with trace amounts of palladium, plus all the other stuff that's usually mentioned, like grain rust and iron and all that stuff. Anyway, I'm done.
Yeah.
Sorry.
Like I also just mentioned that it does seem very interesting, but also a bit strange because I don't think palladium is used by life even today, right? Or maybe it's used by some life still, because I tend to look at I tend to inform my view about the origin of life by looking at life how it is today. Like Nick Lane, of course, often cites the iron sulfur clusters and looks like, it looks a lot like the minerals found in hydrothermal vents, but palladium seems a bit strange to me. I don't know what you can say about it. Yeah.
Yes, I totally agree with you. It is strange. They're not. Sorry, Speed. Go ahead first, and then I'll go after you.
I think it is a mistake to get too hung up on what we see in life right now when we're talking about abiogenesis. Of course, it guides you, but do not insist on it and do not get hung up on it.
Yeah, there's also a point. Yeah, it could be that some things were replaced by life later, but I still think it's very important to explain these peculiarities that life still has. Like, why does it use? Yeah, why does it use these things? Yeah.
I think you should make a T-shirt that says that basically abiogenesis is exobiology, and think about that phrase. Something to consider. Anyway, just my opinion. Go ahead,
so
guys.
I'm actually I'm taking a middle road between the two of you, because even though I agree with Nestle with this kind of principle of continuity, and there are certain really very, very ancient pathways, very in terms of phylogenetics, what's been identified is going all the way back to the root of Luca, of what Luca has, and then trying to extrapolate from Luca to Fuca and so on. And the difficulty of changing these metabolic pathways and stuff like that, the idea of having a major turnover in these metabolic pathways. The paper that I just read by Ralzer in Appeal to Magic, argues that if you're going to make these huge changes to metabolism, you're basically talking about a fundamental turnover of life, turning from one thing to something that's totally and utterly different.
If I can use an analogy, it's like building a house on the foundation, and then halfway between building your house, you replace the foundation, basically.
Yeah,
this is not a house.
So
right.
Yeah, so
it's an analogy, a very crude analogy, but still, yeah.
So I mean, I agree that it's really important to consider that, but at the same time, we should also, I think, acknowledge that life at its inception probably wasn't totally the same as Luca, and the way that Moran and Kaur are using palladium, they're using it as a Kickstarter, because they're only really so far in terms of their presentation, they're only emphasizing it's trace amounts of this that are able to do it. And once this gives you a kickstart, they're talking about the takeover of things like iron and sulfur that are also present in that system, leading to a stable, steady process of it continuing to on-go and develop from there. And that's where you would get your continuity. But the palladium there gives it this extra oomph kick in the ass.
It also one thing. It also reminds me of what Eric Smith says about the roles of different elements, like the elements of carbon, oxygen, nitrogen, and such. They are very unique. They are very unique, and they have very specific roles to play in biochemistry. But when you get to the metals, they seem to be more interchangeable with each other when you get to those.
Yeah. And another thing.
I think Speed wanted to say something before I come.
Sorry, Speed.
Yeah.
I was just going to point out that some sort of exobiology, basically, or exochemistry, could have created an environment where some of these things were concentrated to the point that then the pathways that we're familiar with started up. So, I mean, there could have been an entirely different system that accounted for this new system taking over, right? That's just something to consider.
Yes.
We're dealing with this enormous complexity here.
So
and we have to consider other
like one thing in the hydrothermal system that regarding the structure of life, like it says that the hydrothermal the walls or the membranes of the walls were later replaced by the phospholipids regarding separating the pH gradients. You know, Abyssal, like it's basically the same structure, but then life makes the structure that allows for the separation between the pH differentials. Yeah.
Somebody demo Tangelo out again.
Scott, what's your favorite model so far?
Life.
I am still not informed enough to really pick a favorite model. My idea is just to seek first to understand what each one is saying, and which I still have a sketchy grasp on, and I'll worry about picking a more preferred one later.
Good.
I think picking a favorite at this point is problematic. I don't know. So I'm kind of I'm a theory slut. I like them all.
Heard. And I don't think that's a terrible position to take. It's just that because hydrothermal vents were the first model that really emphasized the whole non-equilibrium thermodynamics thing, that's what hooked me in over there. And there are other models at this point that use that, but just not to the extent or with the level of experimental backing that this model has. So I still think that this one's the best one. But and I guess I'm gonna blab at the mouth right now a little bit because Nestle, you're talking about the principle of continuity. Muchowska in her in that paper on non-enzymatic metabolic reactions talks about the foremost reaction. Talks about how it doesn't have continuity. But the thing about that is that because the foremost reaction is so...
What's the foremost reaction again? I forgot the foremost reaction.
That's what people like even Lane...
Sugars, right?
What's that?
Is it sugars, right, or not?
Yeah, sugars, and particularly ribose, but in very, very low quantities of ribose, which is why people like Lane have concentrated on concentrating ribose through thermophoresis with like that Hershey 2016 paper. And it's kind of funny that that Lane has invoked like the foremost reaction in the past, even though he's a huge advocate of the principle of continuity. But the foremost reaction using that would break a principle of continuity as far as I understand it. It's just that, like, why would we expect life, though, to use the foremost reaction, which is so non-specific for ribose? Like, if it's the case that you get ribose from the foremost reaction at a hydrothermal vent, and then you have thermophoresis concentrating it, we wouldn't expect life to develop the pathway that the vents took to get there, because the original pathway was the chemical pathway was so non-specific, and it relied on the geophysical factors of the vents, of what they're doing in terms of the flow, in order to concentrate the product. And so in terms of like life synthesizing ribose, we would expect the developing pathways to pursue pathways that are far more specific. In that case, like, I think, that's
it's just pathways that look more like the pentose phosphate pathways, or more like gluconeogenesis.
Yes. Yeah.
It's also like that's the thing that I've again with Eric Smith, like he talks about the different domains of life, or not the domains so regarding bacteria. Okay, I'm more about the chemical structure and such. And he says that the thing that seems to be most stable about biochemistry is the core biochemistry with the citric acid cycle and such. And those things seem to be most similar connected to geochemistry. And it seems to be that life, it's basically the chemistry of life is what you get out of those specific precursors in the citric acid cycle, and that's where the specificity comes from. For understand, because even most of the amino acids are directly produced from those citric acid cycle precursors, just emanation of them, and then you have the first amino acids. from those.
How did you feel on your? I wanted to ask you this a while back. How did you feel about your conversation with Taylor when it went down?
Oh my God.
Oh, it went. It was a bit messy because like a car alarm went off outside, so my conversation was cut off pretty early when I had a chance. But yeah.
Yeah, I remember you got cut off early. Didn't you come back later though, and try to at least have a small conversation?
Oh, yeah. Like in the meantime, I was like looking at the paper that was referenced by the person there, and I read the whole paper, but I couldn't find what she was talking about. Like she said, like, oh, they have no idea, and they admit it in the paper. But when I read the paper, it doesn't really say they admit they have no idea, but it does say that it does discuss a thing about what would count as a complete theory. Like, oh, when do we know when we have a sufficient theory for life? And that's the discussion that they were talking about. So they don't say we have no idea. They have only say like, oh, when do we know when we are done, basically. And that's the discussion in the paper. And I was trying to explain it to her, but she didn't get it, I think. But yeah,
she did say that she said that there was no phosphorus on prebiotic Earth
and formaldehyde.
Yeah. She left YouTube, so.
Yep.
That's a smart thing, actually. It's a pretty smart thing.
Yeah, that was a smart thing she did. She wasn't prepared.
I don't recommend.
I mean because YouTube is not a very good place. Yeah, and in general, it's better. Yeah, better for your mental health too.
Well, what's that?
You want to wrap up?
Yep. After I blab about one more thing.
Go ahead. Have at it.
Okay. So I just like a kind of small taste of some of the stuff I'm gonna have responding to Dr. Sadler, because like it's kind of funny. Like I used that paper from Rebo on spontaneous mirror symmetry breaking at the vents, and he dismissed it as just using a computer simulation. But if you guys remember, you were talking before that he actually opens up, his critique using a computer simulation.
Exactly.
Right.
Yeah.
And so, like when you read the paper that he references there, within the article itself, talking about like all these tens of thousands of reactions, many of them abiotic, and then very few being biotic. It actually says within the paper that what distinguishes the biotic products is that they're far more thermodynamically stable. They are far more balanced in terms of their hydrogen bonds. And so like it gives several examples where the actual abiotic messiness is already geared to break down, whereas the biotic ones are far more stable. And so within the paper itself, it's already arguing for giving you reasons as to why life will emerge from a messy environment. I thought that was interesting.
It's what Eric Smith refers to, like the paths of least resistance. Like you have the chemical space as almost infinite many chemicals, but only a few of them will be very stable, and only a few of them will connect to each other in very simple chemical reactions. And the biggest candidate for that is the citric acid cycle, where you have very simple reactions being repeated over and over and over again, and then you get the precursors of life, basically.
Yep.
Yeah.
Yeah. So that's one thing among many. I went back and listened a second time, and I wrote down like 24 main points that he had, and I'm going to put together a presentation. I think it'll be ready in like about a week and a half, because I want to collect like an actual PowerPoint this time, now that I have this laptop back to respond with. So, and because they also like misinterpreted a bunch of the stuff that I was saying. Like they thought I was, and I'm not this particular instance, and this will be my last point before a wrap up. Since you guys are gearing toward the end of this program now, my last one is going to be. It looks like they interpreted me, and I'm not going to suggest that this is like any dishonesty on their part, because like when I went back and listened to it, my wording is really bad. I said, that my exact words were something like, and they've shown step by step, going all the way there to canonical nucleotides, but the paper that showed that got you only 8% yield. And so like they interpreted me as saying that there's like one paper that went from scratch to canonical nucleotides. That wasn't my point. My point was actually that the researchers in general who are focusing on hydrothermal vents, you can find in the literature step by step with these different papers going all the way there to canonical nucleotides. And the paper that showed that the synthesis of canonical nucleotides gave you an 8% yield. And the same thing with, he was saying that I was baiting and switching with the nucleobases. No, like I was actually going toward like the step by step thing when I was getting into that about, nucleobases, the acceleration of the manufacture of ribose 5-phosphate with cysteine and iron and all this other stuff. So they misinterpreted me there, and I think that is legitimately partially my fault because my wording was pretty bad. But no, that was not at all my point. But anyway, that's there's a lot more. I'll come out with it in the next couple of weeks if anybody is interested in it. So yeah, well, I'll take it up from there.
One last thing that I want to mention is regarding that I have seen like a new paper by Nick Lane and colleagues where they showed that it was adenosine triphosphate or ADP or ATP as the it is the only one of the four that will be phosphorylized by like acetyl phosphate, and maybe that's why.
Are you talking about Silvana Pinna's paper, a prebiotic basis for ATP as the universal energy currency? So, that's a good paper, and that's a paper that I'm going to reference in my response to Stadler. It's really going to grind Rebecca's gears because she's all about this thing about the chicken and egg paradox for ATP synthase and how you need ATP. She's going to be very sorely upset, I think, when she finds out that you can get ATP without the ATP synthase. So
I think Sutherland's lab
it's also very straight because life does it all the time. Oh, sorry, go ahead.
I think Sutherland's lab has pointed out some new research on all of that too. I can't remember exactly how it went, but there were some surprising pathways where maybe it was amino acids and nucleic acids that they basically just the same pathway basically accounted for both, and it was very interesting. And I thought they mentioned ATP in there too, but he has some unpublished work that's going to be coming out shortly. So anyway, go ahead, Ness.
I forgot what I was mentioning before.
And I have Bumblebee. The answer for me is Komodo dragon.
Yeah, I'd be with the dragon.
I remember like Rebecca thinks that ATP is the only ATP synthase is the only way ATP is made, but life makes it in very, very different ways. It's not the only way.
Put it out in the beginning, they have this narrative. They're going to show all these one-off. The reason that they call it evidences is because they have these little tiny, they're like little fireflies in the night here and there, where they cherry pick certain things, and they have to provide this. They have to find something to push back on. They have to have this narrative because all of this shit scares the hell out of them, because it seems like the only way they can convince people that God exists is through science. And that's what it was all about. That's what that Rob Stadler thing was all about when you really listen to it. Even though he dressed it up very well in his actual, he has better knowledge than schmucks like Cordova and a bunch of others. But I mean, he was providing a narrative, and that's what they're all about. And that's the point of this.
I released a short video. It was like 25 minutes long before Rebecca aired her show with Dr. Stadler, and I was actually surprised. I started talking about like there were some stupid mistakes that I made in my talk with Rebecca. Most of them are really minor, but there was one in particular that like is serious. It's not an argument that Stadler makes. It's just something that I found on my own, and I'm going to be going into that too. But I was kind of speculating toward the end of the video about how Stadler was, could have like structured his presentation. And I was like basically expressing like, well, I hope he doesn't do this because I know that people who are creationists tend to do these things a lot. And I hope he doesn't do that. I hope he does something a little bit different. And when I went and actually listened to the program, he actually did pretty much everything that I was worried he was going to do. But regardless, he did it in a cordial way for the most part. And he's really like kind of emphasizing that he wants to have a cordial discussion, which is fine by me because he's maintained cordiality, and because the information that he's coming out with, I haven't seen him do anything like obviously deceptive. He's just sorry, go ahead.
Well, I was very impressed with him and his style and his presentation. I think I was more impressed with him this time than all the other times that I've seen him on, like with SFD and stuff. So he did a really good job, I thought, and he seems like a good guy. So I don't know.
Yeah, I wasn't, like I don't share the opinion that you have that you were like, I wasn't very impressed by the overall presentation.
Well,
there's
no,
a lot
presentation, but I was impressed by his. He has more than a shallow knowledge of organic chemistry, anyway, and I was happy to see that, and I liked his style of delivery. But no, overall, I was not impressed with the way he came back at you. So there's a difference.
Yeah, I do. Yeah, I do like his actual presentation style. But yeah, in terms of the actual content, there was like 90% of what he said is stuff that I've heard before, and the only thing that I hadn't heard is what you were asking about before about Fe2+ inhibiting membrane formation, and so I started to look into that. And all I've found so far in the literature is that iron can play a role in lipid peroxidation. So you need oxygen with that, like apparently free oxygen. So that seems to be, as far as I can tell so far, totally irrelevant to Hadean vents. But
that argument right there, that one stopped me cold too, because divalent cations are very present in the cell. It's basically we die very quickly without them, and I don't understand what he was saying.
He's right though when he talks about magnesium. Like even though magnesium's it plays a role and it's been shown to do a bunch of things, it also can do things like degrade RNA, and like that's been shown in the literature on a bunch of different papers. But the interesting thing is that people like Lauren Williams and a bunch of other people decided to take a look at whether or not iron could do the same things, and it does. And so their whole shtick has been iron did this before the great oxygenation event, and once that took place, there was a switch to magnesium.
And the other thing is, if you have those cations present and you have even small peptides, they're going to lock them up pretty quickly, and very easily.
Yeah. So there'll be a lot more from me on what Dr. Stadler had to say in a couple of weeks, and then I'll have the Russell interview, and then I'm gonna go join Taylor in YouTube timeout.
Okay, but when you do produce a video, please email me so that I can talk about it and at least have a chance to look at it before it disappears into the vapor. And also, well, if you'll stick around while I wrap this up, I want to ask you something backstage. So okay. So I think I'm going to end it. I want to keep it under 2 hours.
If I may, I want to explain this figure that I was sharing, like about the claim.
Go ahead.
About the claim that like ATP is only made by ATP synthase, but in this figure from the book that you also have, Speed, The Origin and Nature of Life on Earth by Smith and Morowitz. Like this picture summarizes life with respect to the thermodynamics. Like you have three very significant types of disequilibrium. You have the redox disequilibrium from the environment, or generated by photosynthesis, where you have electrons donated by donors and accepted by acceptors. And you also have the proton gradient across the membrane, and you have the phosphate like ATP or acetyl phosphate. And it turns out that these are connected by different mechanisms, and one of these mechanisms is done by very small molecules called substrate phosphorylation, where redox is connected by the phosphate. But the other systems, this one is by intermediate size molecules like quinones from redox to protons. Like it's the I think it's the oxidative phosphorylation pathway, where you have like proton pumping and such to create the pH gradient, and from that you have the ATP synthase. So in this way, it's very complicated, but in this way, it seems to be more simpler and more similar to what is going on in like prebiotic conditions.
Yep.
Yeah, so it shows very very different systems that life relies on. But yet they are still connected.
Eric Smith is awesome. Him and Morowitz are just such good writers, such good thinkers. Like they have papers going back to like 2009 that were that just spelled out like an RNA peptide world so well, like way before all these other researchers really started picking up on it. Those guys are just awesome. They're just so freaking cool. They really have their stuff together. So there's a couple of things here. The one commenter talked about glyoxylate shunt, and that's also been shown to be catalyzed non-enzymatically using metals and heating. I just got done reading. You go check out. There's a paper, if you're interested, you can read it. It's by Marcus Raulzer. I just finished reading it myself. It's called An Appeal to Magic. Published, I think, in 2019. So R-A-L-S-E-R, Raulzer, and An Appeal to Magic with a question mark. If you put that into Google Scholar, that article will pop up and you can read it.
Or you could just look at my description. I have a link to it out there.
Oh, all right, great.
Okay. Okay, can we wrap up?
Yes.
Can we comment real quick on Mr. Jetty 89's question?
Oh yeah, go ahead. Does somebody want to handle that? This Palladium? Go ahead.
I don't know, but the Hartpreet Kaur paper is currently under peer review. So within like the next, hopefully, few months, it'll be out. And so it should, it's going to be a paper published under her name. Her last name is Kaur, Kaur. And also Bill Martin is a co-author on the paper. So if you keep your eyes out for her results working with Palladium, it should be available within the next few months, I'm hoping.
Now, is Palladium or Palladium, is that what they use to assassinate British agents?
Probably.
They should.
Yeah, I think there was like a British, some sort of British agent that was assassinated by the Russians like that. So.
Oh my god!
Yeah.
That new comment by Otenslo is just like pure.
Oh my!
No self-awareness at all.
Yeah.
Guy's such a clown.
That one. Because photosynthesis.
Yes, no self-awareness.
Nope. Yeah. Yeah. Otangelo, we love you. Anyway, okay, I'm going to wrap it up. And thank you, Ness and Dessel. This would have sucked without you guys.
Wait a minute.
What?
Did Ness ever answer Bree's Panda versus Komodo Dragon question?
Dessel did.
I did not notice that.
If you're Nestleg, if you're stuck in a bathroom and you have to choose which one you're stuck with, a panda or Komodo dragon, which one would you choose?
Bathroom stall.
In the bedroom?
Yeah, in the bathroom. Yeah. I went with the dragon.
I think it's a trick question, so I don't know. It's probably like, oh, I choose the panda, but then actually the panda is more dangerous. Like I don't know. It will be going like that.
I'm going for the dragon. Okay, guys, we're gonna end.
All right, thank you everybody for coming and listening to everything tonight.
Yep.
We appreciate everybody out there.
Goodbye, cruel world.